Okay, so in this part, we're going to talk about increasing and decreasing continuous functions and their inverses. So in particular, we're going to show that a strictly increasing continuous function on an interval automatically has an inverse, which is also increasing and continuous on that interval. Before I get into that, just a couple sort of basics. For one thing, I want to remind you of what I was saying earlier, because I know I've been using this, but I just want to make sure everyone remembers that. So if A is a subset of the domain of F, then we write F of A for the set of values of F of X, where X is in A. Okay, so you just evaluate F on every point in A, collect the results into a set, and there you go. Okay, as a as a basic consequence of this, what we can say is if a value y is in F of A, right, then there exists an X in A. This might seem trivial right now, but it's actually something I've seen people get tripped up by this. Trust me, like a lot. So if simply membership in this set, okay, membership in this set guarantees the existence of some X such that F of X equals Y, right? There are a lot of times when we use this kind of thing and people attribute it to the intermediate value theorem when it's not at all. This is not the intermediate value theorem. This is literally just by definition of F of A, okay? Okay, anyway. So now also we say F, let's say function F with domain of F in R, real valued, of course, is increasing, strictly, I guess. Strictly increasing if for all x less than y in domain of F, we have F of X less than F of Y, right? Simple enough. And similarly, decreasing F of X is greater than F of Y, whenever X is less than Y, of course, right? So this is for strictly increasing and strictly decreasing. Weakly increasing or just increasing, probably by default saying increasing would refer to weakly increasing, although for this conversation, we're really only interested in strictly increasing and strictly decreasing functions. So for a weakly increasing function, this is just less than or equal to, so it can be constant for certain portions of the domain. But yeah, anyway, so this is increasing and this is decreasing. In general, a function F is 1 to 1, or as I prefer to say, injective, if for all A, B in the domain of F, F of A equals F of B if and only if A equals B. Okay, so basically, in a few words, a one-to-one function is not allowed to map two different inputs to the same output value. There can be no collisions of output values between different inputs, okay? So one-to-one functions, a one-to-one function has an inverse with domain F of domain of F. Okay, which is also called the image of F. Okay, I should be really careful about this. This is technically not how inverses work in general. Okay, so in a broader mathematical context, a function does not have an inverse just if it's one-to-one. A function in general, in like math in general, only has an inverse if it's both one-to-one and onto, meaning it's surjective. In our case, for real analysis, okay, a function is sort of invertible if it's one-to-one in the sense that you can define an inverse function whose domain is just restricted to the actual set of output values of the original function f, okay? So even if f is not, surjective onto its codomain, we don't really care about that because we can just take whatever values f actually does produce, collect those into a set, and then call that the domain of f inverse, okay? For some reason, that's more conventional in real analysis and very much not conventional in other parts of math, so I don't want you guys to get confused. In general, this would be kind of a sacrilegious thing to say, but for us, we're gonna say that if a function is one-to-one, you can define an inverse, quote unquote. Okay, so that's just a kind of a technical point here. Okay, but of course, this one-to-one or injectivity property is something that definitely exists throughout all areas of math, and it's defined the same way everywhere. So anyway, okay, so with that out of the way, let me state the main theorem we're going to prove in this section here. So 15.4 theorem. Oh yeah, and note that if f is increasing, if f is strictly increasing, then f is injective. Okay, because if f is strictly increasing, then for any two distinct input values, one of them is going to be bigger. So then the output value at the bigger one is going to be bigger than the other output value. So they can't be equal to each other, right? So if it's strictly increasing, then it's definitely injective. So let f be strictly increasing and continuous on an interval I, then f of I is an interval J, and f inverse so the inverse of f is a continuous, strictly increasing function on J. Yes. Okay. This is more or less, I mean, they phrased it slightly more delicately in the book, but this is basically what we're going to try to show. So what they do is they kind of delegate most of the proof to a slightly different thing. So what they say is, okay, if f is strictly increasing, then clearly f inverse exists on J because f is one-to-one, right? So since f is injective, f inverse is increasing strictly because if y1 less than y2 in J, then say x1 is f inverse of y1 and x2 is f inverse of y2, right? i.e. f of x1 is y1 and f of x2 is y2, right? Then clearly x1 is less than x2 because otherwise y1 would be greater than or equal to y2, which is, I mean, just by contraposition, that's impossible, right? So yeah, if f preserves ordering, that's another way of thinking of an increasing function is just one which preserves the order of its inputs. So if f preserves ordering going one way, then the inverse should preserve the ordering going backwards, right? That's sort of straightforward. So then what they say is, then f inverse is a strictly increasing function on J with f inverse of J, f inverse of J equals I, where I is an interval. The next theorem shows this means f inverse is continuous. Okay, so basically there's another theorem that we'll prove now, which says that if you have a strictly increasing function defined on some interval, and the image of that interval is another interval, then that actually means that the increasing function is continuous. Okay, so this is actually kind of, they say this in the book. This is a partial converse of the intermediate value theorem, because basically it says that f is increasing and has the intermediate value property means that it's continuous, right? The intermediate value theorem tells us that if f is continuous, then it has the intermediate value property. So the converse of the intermediate value theorem would be to say, if f has the intermediate value property, then it's continuous, right? That actually turns out to be false. So the full converse of the intermediate value theorem is the intermediate value property implies that f is continuous. This is false. Okay, they mention an exercise. I don't remember if I put it on the homework, but either way, I think we'll probably cover it at some point. So yeah, the converse of the intermediate value theorem is false, but this is a sort of a partial converse where you add an extra assumption about f, and then it becomes true that if it has the intermediate value property, it has to be continuous. So let's just look at the proof of that real quick. I'm gonna make a cut so I can draw kind of a sketch here. So, well, let me state the theorem and then I'll draw the sketch. So this is theorem 18.5. So let G be a strictly increasing function on J, and G of J, or such that, let's say, better wording, such that G of J is an interval I. Then G is continuous on J. Okay? So, all right, I'm going to draw a picture. Okay, so here's the sort of sketch of this proof. And I went ahead and drew the diagram. This is like the graph of G here. This is J down here. I drew squiggly lines because we don't know whether these endpoints are open or closed, and it doesn't really matter. And same thing here. So anyway, and it also actually, you can make this argument. I mean, the argument will work even if some of these endpoints are infinite or not. It doesn't matter, but I'll just consider them to be finite for the sake of the picture. So basically the way it works is, okay, we let x naught be in J and assume x naught is not an endpoint because the endpoints are irritating and tedious, but not difficult. So basically, to really properly, you would have to break into like 3 cases where x naught is like the left endpoint, x naught is the right endpoint, or x naught is somewhere in between, and make a slightly different argument for all 3 cases. But the differences are so small that we're just going to like consider x naught to be inside the interval in the interior. Okay, so then that means that g of x naught is right. That means g of x naught is not an endpoint of I, because obviously if x naught is not an endpoint here, you can find points to the right and you can find points to the left. So there have to be values of g that are bigger or smaller than g of x naught. So g of x naught is not an endpoint of I. So g of x naught, not an endpoint I, means there exists an epsilon naught greater than 0 such that g of x naught minus epsilon naught g of x naught plus epsilon naught is a subset of I. Okay, so that's what I've drawn here. This is, epsilon naught here is the sort of half the width of this band, right? And so the idea is that it's like, okay, we'll just find, we'll find deltas for any epsilon that's like smaller than epsilon naught, because for big values of epsilon, if we just change to a smaller value of epsilon, like if we find a delta for a small value of epsilon, that same delta works for all bigger values of epsilon. So basically by finding delta for any epsilon smaller than epsilon naught, we'll find it for all the values of epsilon, basically. Okay, so so let epsilon greater than 0, epsilon is less than epsilon naught. Then what we'll say is, okay, because right, because oh right, because okay, so then g of x naught minus epsilon is in I. Well, yeah, g of x naught minus epsilon and g of x naught plus epsilon are in I. There exists, x1 and x2 such that g of x1 equals g of x naught minus epsilon and g of x2 equals g of x naught plus epsilon. Okay, so remember, this is going back to the logic I said over here way back in the beginning. So here, if something is in f of a, then there has to be a value which actually produces that. There has to be an input that produces that output value, right? If an output is in f of a, there is an input which produces that output. That's what we're using here. So this is not the intermediate value theorem. We're just saying that so this g of x naught minus epsilon is in this interval, right? Because epsilon is less than epsilon naught. So this is in this interval, which means it's in I itself, right? I is g of j, right? So g of x naught minus epsilon is in g of j. That means that there exists an input which produces g of x naught minus epsilon as an output value. Same thing for g of x naught plus epsilon, right? So let's say this is epsilon actually instead of epsilon naught. Okay. Then, so if this is epsilon, so epsilon naught might be bigger, but it doesn't matter. Then basically, in this graph, x1 would be over here, and x2 is over here. Okay. So basically, the idea is, right, we want to find a radius around x naught such that the graph stays inside this band. But what we can do is, well, now we have the points where it passes in and out of the band. So whichever one of those is closer, we'll just take our radius to be like that. So take delta to be the minimum of x naught minus x1 and x2 minus x naught, right? And we know that x naught has to be bigger than x1 because g of x naught is bigger than g of x1, right? Because g of x naught is, well, g of x1 is g of x naught minus epsilon, right? So g of x naught is bigger, and g of x2 is bigger than g of x0, so x2 has to be bigger than x0, so this is also positive, right? So they're laid out in this order on the x-axis. And so then, from the graph, I'll just say the graph shows, I mean, you can show in symbols, I think they write it out in symbols in the book, but, you can see from the graph that for let's say, for x in x naught minus delta, x naught plus delta, we have absolute value of g of x minus g of x naught less than epsilon. Okay, so that kind of completes the proof of that this g is increasing, and then of course remember that the whole reason we did that was to apply it to this situation where g is actually like playing the role of f inverse, or rather f inverse is playing the role of g in the theorem we just proved over here. Okay, so g is like f inverse over here, so that means f inverse is continuous because these are the hypotheses of that theorem. Okay, so in the next and final section, I will talk about how injective functions have to be either increasing or decreasing. Injective continuous functions.